Described in 1845 by Gustav Kirchhoff, Kirchhoff's laws for current and voltage are two equalities that deal with the conservation of charge and energy in electrical circuits. They are widely used in electrical engineering today. Kirchhoff's current law, the principle of conservation of electric charge, implies that at any node or junction in an electrical circuit, the sum of currents flowing into that node is equal to the sum of currents flowing out of that node, or the algebraic sum of currents in a network of conductors meeting at a point is zero. Let's take a closer look at how electrical currents travel in this simulation. This simulation contains 4 loads. There are 2 parallel branches. Branch 1 contains load 2, and branch 2 contains load 3 and 4. There are 2 nodes that are the junction points between branch 1 and branch 2. All of the circuit's total current flows through load number 1, which is indicated by the large red dot labeled IT. When IT reaches node number 1, the circuit's total current splits into 2 currents labeled IB1 and IB2. The amount of current entering node 1 equals the sum of the 2 currents leaving node 1. Notice that the current does not split equally in this simulation. IB1 is larger than IB2. This is an indication that branch 1 of the circuit has a decreased opposition to current flow compared to branch 2, or simply put, branch 1 is less resistive than branch 2. As IB1 and IB2 enter node 2, the 2 currents add, and the sum of the currents exit node 2, which is the circuit's total current, IT. Kirchhoff's current law states that the sum of the currents flowing into a node equals the sum of the currents exiting the node. Kirchhoff's voltage law, the principle of conservation of energy, implies that the directed sum of the electrical potential differences or voltage around any closed network is zero, or, more simply, the sum of the electromotive forces in any closed loop is equivalent to the sum of the potential drops in that loop. The algebraic sum of the products of the resistances of the conductors and the currents in them in a closed loop is equal to the total EMF available in that loop. If we were to take voltmeters and measure the voltage drop across each resistor, stepping around the circuit in a clockwise direction with the red test lead of our meter on the point ahead and the black test lead on the point behind, we would obtain the following readings. The voltage between D and A is positive 45 volts. The voltage between A and B is negative 10 volts. The voltage between B and C is negative 20 volts. And the voltage between C and D is negative 15 volts. The individual voltage drops add up to the total applied voltage, but measuring voltage drops in this manner and paying attention to the polarity or mathematical sign of the readings reveals another facet of this principle, that the voltages measured in a closed loop all add up to zero.